Good evening, everyone. Thank you very much for joining us today. We are very excited for today's talk because we have someone very special with us. This is our last talk and astronomy event for 2016, and I'm very pleased to see that our community has participated very well in our programs. After this talk, we have a stargazing event for you, so please go to the Montgomery Hill Observatory and enjoy a beautiful stargazing night. We have moon with the Venus. It looks beautiful there. So our today's talk is, our speaker is Dr. Rosalba Bonaccorsi. She is an astrobiologist of SETI Institute's Carl Sagan Center at NASA Ames Research Center. Rosalba obtained her PhD in geological, marine, and environmental sciences from the University of Trieste, Italy. Since 2005, she has expanded her Mars-like environment and research in very dry desert regions worldwide. For the past 10 years, she has been science team member and field instructor during NASA's Spaceward expeditions to remote places, including the Death Valley National Park, Mojave Desert, Antarctica, Atacama Desert in Chile, Australia, New Zealand, Israel, and Namib Desert. So please welcome Dr. Rosalba Bonaccorsi.
Thank you for being here. I'm very excited to be here. Also very jet lagged, so I hope you bear with me and pardon my strong Italian accent. Let's go. So, science expedition. Everybody came here?
No.
Okay. 1, 2, 3.
No.
Probably. Okay. 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 Let's start again. So, I've been in several places for both scientific interest and pleasure, because the two things are, colliding together in my life. So let's go about the outline. So we talk about astrobiology-driven search for life elsewhere, and then we do some expedition examples around the globe. And we talk about a little bit life detection methods, not because I wanted to make you very, very bored, but because the aspects of life detection and search for life are really related. And then I offer an example of the latest expedition that's been done in India, in the Kashmir region, in Ladakh, in the Himalayas, which I will show a little bit a nice movie that we just done there. So why do field science expedition to planetary analogs? Well, NASA, and not just NASA, has been very, very intrigued about the idea of finding life on other planetary bodies. Are we alone in this universe? Are we alone in the solar system? We don't know yet, but it's worth to start research. So also there is the NASA vision for space exploration that involves both mission, they are robotic at this stage, but also going to be manned. So man means that we have been on the moon, but also we hope to go very soon to Mars. And why not also in other places, very interesting places in our solar system. So analogs environment, what are they? But why we're doing this type of research? So we use analog environment to explore and learn. So what about exploration? Exploration is excitement of going to a place where no man has been before. Probably you recognize this famous quote. So it's also for testing technologies, not just technologies, but also methodologies for doing things on Mars-like environments or planetary-like environments. And also for training, who are supposed to be trained? Well, everybody's supposed to be trained, even scientists, but particularly educators and people like you, and people also that probably not going to explore this place, but people are taking charge and teaching the next generation, because it will be the next generation that will be seeing and maybe step their feet. Maybe you guys that are here on Mars first, and maybe on Europa. Maybe next life people could go on those places. Maybe by 30 years, by now 50 years, 100 years, and so on. And then also to engage. Engaging is very, very important because it's us as a citizen of the world that are going to be responsible for asking our administrator to continue research. Research doesn't come cheap. It's funding, and it's engagement, and it's training, and it's not just about money. It's about all the entire infrastructure that will lead us to explore our solar system and getting out from our native planet. So, okay, there are several places in our solar system that we are very, very keen to explore. Well, we have Mars, of course, as a superstar because it's so close to us that we can get there in about 6-9 months. But also there are very super cool places. And these very super cool places are icy moon of Jupiter, like Europa. Maybe some of you saw the movie Europa Report. And it's just a cool place where to be. Why is a cool place where to be? Because there is an ocean underneath a thick crust of ice, which means there's real water there. And life, as we know it, needs water, so a place where there's the entire ocean, which means it could be an ecosystem down there. Another place is super, super cool beside Europa is Enceladus. It's another icy moon of Saturn. And Enceladus has a plume coming out from the southern pole, like here from the Cassini image is 2015. So there's real water, not just from beneath the ice, but coming out. And this water contains organics. And so we have organics, we have a water, we have probably a complex hydrothermal system beneath an ocean. And so there are mission plans to go and fly by to the Enceladus lower plume and catching up the particle of ice that is coming out and looking if there is more complex organics like lipids or amino acid or maybe even dead bodies of salts that are being ejected from the geyser they are ejected from here. So another alien planet could be, you know what? Early Earth. Okay, early Earth was very different at the beginning, 4.8, 4.6 billion of years ago. Continents are totally messed up. They changed over time. They expanded. They collided again. Atmosphere was probably different. Maybe even the chemistry was different. So Earth was a truly early alien planet. So what we learn today from extreme environments and anomalous environments is some clue about how early Earth was. And then, of course, Titan. Titan is another cool place where we have a liquid hydrocarbons. And that's a first example of a liquid which is not water. And we have an entire geology up there and another geomorphology where, it could look like Santa Barbara coast. If you look at those pictures, it's just that it's not an ocean made of water. And maybe it's too early to be life there, but we will never know. I mean, it's full of surprise. And then, of course, extrasolar planet that, it's amazing. It's increasing the number over time of these planets, like much bigger than Earth, of supergiant planets that have strange morphology, strange ecology, strange atmospheres, and people are looking at those places. So search for life, another word. Why is so interesting? Well, we know today just one example of life. Life is based on the basic building blocks of life, but unfortunately we have not been out of ourselves to see if there is another example of life. life as we probably don't know it. And we are looking for different kind of biochemistry out there. Oops. And life might or might not be common in the universe. But is life common in our solar system? We don't know yet. We can just figure out that if we have ingredients for life, if we have a suitable environment for life, then we might even have some form of life. So, and we can learn a lot about the Earth at the beginning, how early life was. We don't know yet. There's been so many speculation about that. So this is why it's so important looking for life outside of our planet and our planet alike. So this is probably one of the last very technical as well. So the search for life. This is where everybody gets sometimes confused. Because sometimes we talk about actual life, so life detection, actual living organisms, but also NASA, what has been looking for is potential for life. Looking for potential for life or ingredients for life, but not actual life. It's all concerned habitability. It's a big world in the search for life, because it's based on, look at basic stuff. Look at the condition for life in terms of temperature, liquid water, energy sources, pH, degrees of acidity, and radiation environments, etc. It's easier looking for water on the planet, or evidence of water. It's lesser easier, much more difficult looking at actual living organisms. Between looking at actual living organisms, so happy, moving, and reproducing microbes, and ingredients for life supporting those microbes, there is a world, an abyss between. And this is looking at proxy for past and present life, which means looking at biomarker. There could be mineral biomarker or organic molecules, dead bodies or fossils. They don't tell us that we have living things, but they tell us that we might have had living cells. And so let's look at the preservation of biomarkers. So all these streams, they are leading to the clues for search for life in the solar system. In the bottom, we see some example of where this type of search leads. So actual living organisms at this stage are not the target of Mars. So, but they were the target in the past. The Viking missions were looking for active metabolism, but they were not found there. Okay, so there was a big disappointment. This is why NASA and the agencies wanted to play safe, because it would be another big disappointment if we go to Mars today and we don't find anything. It's very difficult, theoretically, that life could be still alive on Mars. This is why the mission that we have today, so Mars Science Laboratory, that has been so successful in finding some organics there, or evidence of life, or even the Mars 2020, they're not going for life detection there. Who is going for life detection? Well, it's going for life detection who is looking for places with liquid water. This is why I'm so excited about Enceladus, because Enceladus will be a life detection mission, because there's actually water and organics in great abundance there. So that is the new frontier. Much more to be excited. I will be disappointed that there will not be on the 2020 mission detectors for life. Not at all. So why Mars? Well, Mars is our closest target for looking for past life. There was a lot of evidence in terms of geology for past life. And also we have, sorry about that, we have an atmosphere with the carbon dioxide and nitrogen. Yummy stuff, because these are the ingredients for life. Okay, our proteins, amino acid, the DNA, RNA are made of carbon, oxygen, nitrogen, and sulfur, and other ingredients for life. This is in the surface of Mars, and also in the atmosphere of Mars, there's plenty of that. So there is also a potential for preservation of life because we have a lot of minerals that are preserving organics. And I will talk a little bit more about those in the next. So we go to different places regarding Mars, which is now our target, that are not just analog for our Mars today, but are here's Mars today. If you go back to the past, we have a different kind of Mars. We have a cold Mars, and we have a green and Mars that was at the beginning of the life and the sort of existence of our solar system. Mars and Earth were sharing, and let's say sharing the presence of water and the fact that probably was a thicker atmosphere. Not quite sure about that, but we know that there was much more water at the beginning than today. So when we look at the analog environment, we have wet Mars. So the Canadian Arctic could be one example, wet Mars, the Rio Tinto, all places where, or Pilbara in Australia, or even the Mojave Desert, where we don't have a lot of water, but we have water enough that could be very similar to what was Mars at the beginning, with maybe ocean, maybe lakes, maybe rivers, maybe just puddle. And then we have an example of a dry Mars and cold frozen Mars in Antarctica. So, and those environments are also in these environments also we have analog, not just for Mars, but all other icy moons where we have a thick, up to 3,000, 5,000 meter thick ice that encapsulate and cover liquid water. And then we have a Mars as today, it's frozen and cold, but the water is trapped underneath. And the best example for this is today's University Valley in Antarctica. But also we have other interesting examples for that, for a dry Mars. Why it doesn't go? Okay, so in terms of planetary analogs, what are these analogs? Well, we have a Mars-like geology or planetary-like geology, where for geology I mean a bunch of things like terrain, landscape, rocks, sediments, and minerals. There are different degrees. And then we have a climate. Climate's a liquid water, so the climate is the result of temperature and presence of water on a planet. This combination that gives the different climates we have. And then this combination of climates, which means ocean to ponds and their time scale, plus Mars-like geology, terrain, rock, sediment, minerals, are producing the condition for the existence of life. So, I'm presenting a bunch of pictures that I won't tell you where they're from. I will just make you guessing where these pictures were taken, okay? So, this picture is very, very arid place. You see no plants. You see a lot of basaltic rocks that are scattered around. You see kind of sky that, kind of blue, but don't be too much the sea from that color. So here are some example of sediments. Sediments are rock. Layer sediments has been deposited by water or by wind. Other sediments, there are dunes. Dunes were made of different materials, like some dunes are made by fragmental shells on other planet when you go to the beach, or they are made by quartz, super white quartz. If you go to coastal California, you can find these super white beaches. They are made by pure quartz. Some beaches can be black because they're made by lapilli, volcanic stuff. And some beaches are red, or some sands are very red. So where has been taken this? Is any analogy with the previous field I took? So these dunes are kind of white. They are made by volcanic cinder. They're dunes are made by volcanic cinder on Mars, or at least scientists do believe that those white color are related to the minerals. They are volcanic tuff. So, okay, a clue here. This is the Yellowknife Bay of Mars, currently in the Gale Crater. So, I omitted to put a picture of Gale Crater, but you can go on the internet and type Gale Crater, and you will, see the context of this. So this is Mars from it. Let me see where the dunes are supposed to be. Okay. I'm fighting with these things. I'm hopeless. Sorry. It's not working. Can you go back? Okay. Okay. Go back to this. Okay. So I cannot jump too much, but here in this region there would be those dunes you've seen before. Here you have a clay it's from a lake that probably was on Mars 2.3 billions of years ago. And here you have a mound that's made of layered sediments of sandstone and claystone. They are different from this. This has been deposited in the shallow water. This has been deposited in 100 meters deep water. So shallow waters was lasting for maybe 1,000 years, maybe a little bit more. Deeper lakes were lasting maybe for 100,000 years on Mars. This is the same things that happen also on our planet. The shallower, the least time the water can persist on a planet, either on Mars, on Earth, or another planet. So I will show some more examples. So here's Atacama. Why Atacama? Atacama is the driest place on Earth. Just 2 millimeters of water per year. And sometimes it doesn't rain at all. Sometimes it rains just for a few minutes. This is why the 2 millimeters. For comparison, California, where we live today, is about 700, 800 millimeters. I know millimeters are not inches. Sorry to make the conversion for me. And so this is the Chile, Atacama Desert in the northern part of Chile. This is the Pacific Ocean. And you can see here we have moisture coming from the Pacific Ocean. And here is the moisture in the Amazon basin. But neither one can get into here because they are a chain of mountains. So we call double rain shadow. So basically the moisture gets squeezed even before it can get into the desert. So here's this young guy. This is a desert station where we have been running expeditions since 2006. And here's a nice space shuttle view taken in June 1990. So here's our station. Here there are plants just because there's water underneath. There's a lot of water underneath the desert on our planet. So this doesn't conflict with the fact that the surface of the planet, paradoxically, are very super dry. You could drown on that reservoir of water, which almost happened to us once. So this is what scientists do. I mean, scientists look at microbes and look at minerals on the surface of this place. So there are several instruments. And this guy here is looking at variation in the temperature, difference in temperature between nights and days, which I do also, but not in this desert, in another desert in that valley. So this is Aaron, and Aaron is now doing for NASA little comics about astrobiology. He became a very famous guy. So Atacama Desert. So the Mars-like soil of the Atacama is as such that doesn't preserve organics because it's too dry. There are a few microbes too, but these microbes are very difficult to cultivate. And this was to culture, but no worries because microbes are always very difficult to culture. So just 1% of microbes presence in any soil could be cultured. So we have to look at other proxies for living cells that could be called biosignatures. It means organic molecules that have a specific lifespan that can tell us if microbes were alive or they are just, fossil molecules. Some molecules can last a lot, 1,000 years, even millions of years. Some molecules last just 5 months. If I find those molecules integer, means that those come from life that just died. So this is what we do. So Atacama is nice analogs, biological analog for Mars, because if we were going there and grabbing a scoop of that soil, we were probably not seeing any microbe as happening on Mars. So this is another example of geomorphology. So you see here Mars, this is the Gale Crater, this is another gully. We see like water with sculpture, the morphology. And here there is this Gale Crater, okay? This is clay stone, made of like the clay you play, the kids play, and deposited by the water. And here's a place that I really love a lot. It's from Gale Crater in Death Valley National Park. I will show you more of that. But they're nearby identical. Now back to Atacama, life. So Atacama is also considered the last outpost for life. Why? Well, it's so dry that microbes can really live out there because it's too dry, there are oxidants. But this is what you see. These are salt. And this salt has been deposited millions of years ago, 50 millions of years ago, or even earlier. And here is just an example of how the wind creates sculptures on this soil. Okay, it looks like rock, could be marble, but believe me, it's salt. And if you start hammering on these or scratching the surface of this, you will see this. Okay, this is the surface. And this green stuff, what this green stuff is? Well, I'm very curious, guys, so I had to taste it. I knew there were cyanobacteria, okay, but it tasted really like lactose, that kind of thing. And people say, no, don't do that, just, you're going to get sick. Oh, well, yeah, I'm curious, and just tastes good. So, this type of cyanobacteria that cannot live on the surface of the Atacama, right? Because it's too dry. So, and also scientists believe that salt is not friends of life, right? So it's very, very difficult that life can survive salt unless it's adapted. But what a colleague of mine found, Alfonso Davila, who works with me at SETI Institute at NASA Ames and loves a lot Atacama, found this. These are stain cells. They're red. Why red? Well, not because they're communist, but because they're alive. So the staining made them that they are red instead of being green. And here is the salt. And you can see the salt. It tends to be, here you have a larger scanning electron microscope. You have a larger view of this. They look like a grape. And here's the salt. And you can see the salt crystal is kind of moldy. Why? Because the salt scavenge and absorb from the air the moisture. So what's happening is, even if you have a planet, or like Atacama is very dry, has just 1% of humidity in the air, relative humidity. But all the humidity can be scavenged, absorbed by those that salt that calls the liquefaction property. So you put some salt, they just become hygroscopic. They absorb water, they melt, as you would have a crystal of ice that's melting when you take out from a refrigerator. So this melting produces a very, very tiny layer of water, and this water really helps a lot because it makes those microbes alive. So this is an example that Atacama, the driest place on Earth, can tell us. Also, Alfonso wrote a nice paper where he demonstrated that on Mars, do you remember the different stage of Mars? So Mars over time would become a little bit wetter because the axis of the planet is tilting, which means over time, in about 20,000 years, Mars will be a little bit wetter. Which means that if you have a bacteria, they are dormant, in there, and there is salt on Atacama too. The same condition we saw about that we see in the Atacama today could be found on Mars, which means salt could be the last outpost for life on Mars. So I will go over it a little bit quicker. So it's another example of life living in rocks, when geology marry biology, or biology marry geology, whatever, whichever comes first. So these are sandstone in the other driest place on Earth, but this is also cold because it's in Antarctica, so it's an example of cold desert. No precipitation, low temperature, no water, but look at here. If you start hammering these rocks, you see that there's a lot of grains sustained on sandstone. This is Bacon's Valley, is an important geological outcrop. The mountains made of this sandstone. And we have a life. We have actually an entire ecology there. We have black microbes, green microbes, yellow microbes. They all live together, associated with together. The greens use the sunlight and then produce organics. They're eaten by those microbes that need organic, the heterotroph. And you guys are heterotroph, by the way, because you just had a nice dinner, I hope. And autotroph are the green guys, and you see green guys feeding the black guys and the red guys. And here we have another example from the desert. Namib is another place on Earth where we have, let's say, a little bit more precipitation, 10 millimeters of water, but the majority of water doesn't come by rain, but comes with moisture. It's present as fog. And here we have some microbes and cyanobacteria and the lichens. They are present in rock. Others can live under the rock as hypolytic. So rock preserve and protect from radiation microbes. And microbes can live beneath the rock because they can still get some light and get protection at the same time. And these are other candidates, potential candidates on planetary deserts beyond our planet. So follow the water, that is the key ingredient for life, one of the main ingredients for life. So part of my work is just chasing storms. Why do we chase storms? Because I chase a puddle of water in very right places, like the valley in the Mojave Desert. So after big rainstorms, which characterize our desert. So our desert are reflect the condition of presence of water. So the presence of water is always a balance between the precipitation and evaporations. Some places like Atacama could be very dry because it never rains, so rain very little. Other places like Death Valley or the Mojave Desert, nearby us, more or less, are 50 times more humid than the Atacama Desert, but have also a lot of evapotranspiration. So you have a lot of water that get it away by evaporation. And for instance, if you take a shower in summer in the Mojave Desert, you will dry it up in 3 to 5 minutes, okay? And you need to drink a quarter of a gallon of water not to die, because that's exactly what your body is evaporating. So the Death Valley is very dry, particularly in summer, just because it gets a lot of evaporation. And it gets some sporadic storm, but storms in the desert comes all together, which means in a few hours or in one day you will get the entire water that you could get in a few months. So flash flood always are something that you want to avoid. Sorry about. Let's see. One more back. Okay, this one. Okay, so this is the water, ephemeral pond. Okay, think about Mars at the very beginning. Think about a little water that came together, produced a pond, and to my surprise, I took the water, and after a few hours of precipitation, they were these guys. These are who? Other cyanobacteria. But they're not like the cyanobacteria I showed you before. They do need pond water. So like a mini ocean available to them, but they don't need it for a long time. They just need it for a few hours. This is the beauty of it. So life is just a little bit amount of water, even the desert. And as soon as they get water, the dormant life come out, do all the things that microbes like doing, like eating, reproducing, looking at their, living little spores with tiny life that can be dormant. In this case, for years. In case of Mars, could be millennia or even millions of years. The same idea does apply to the Atacama Desert here. Before the rain, after the rain. This happened every 15 years, 10, 15 years, every El Nino year. This year also the Death Valley bloomed. But for Atacama, it's even more precious by considering that it has just so little water that not even microbes could live there. So other astrobiology field expedition, how much time we have? Okay, so I will just show you some example of what we do and how we do it. So this was a program called NASA Spaceward Bound, and there's a link here. It's still active. That's a sort of archive for all expedition we did. And there's a lot of materials about what I said, about life in desert and different things. And the planetary research, the search for life by NASA, and more. So this was an educational program that's been developed by NASA in 2006, and it ran for 3 years. The basic idea was going to a place for doing astrobiology-related research associated with the search of life in an analog environment, and bring with us teachers, preschool or in school or in service, pre-service or in-service teachers, and learning with scientists the methods and the theory and the practice hands-on in the field, and then bringing the lesson back to the classrooms. That was the most powerful thing, having these super cool, excited, functional things made by diverse array of people. So we did many. Remember the first map I showed? Those were most NASA Spacebound expeditions. So we had one in Australia, actually 2 in Australia. Why Australia? Because in Australia they are the oldest fossil on this planet. And so it was originally, this program was originally funded by the the Science and Exploration System Mission Directorate. And we wanted to train the next generation of space scientists, and scientists just work with teachers. So we have here teacher, scientists, students, and we communicate, we explain how to take samples and why we need to take samples. And here's another example. This was in going on the Western Australia. So we were looking for stromatolites, but not just stromatolites, but we want to have a trial. So remember the idea of testing. So we test instruments. In this case, we are testing spacesuits to see if astronaut geologists could perform under those conditions. It was very hot, and the terrain was very rugged, like Mars-like, in the Martian, you have to climb. And also, if with the suit we could perform properly. Right, guys, it's very, very hard looking at something, a geological sample, where you're wearing that thing. I mean, it was really struggling. I barely was able to move, and I was barely able to see what was, my geological sample. And then we did produce a nice paper that, of course, shown that with suit, everything is much more difficult, okay? But we need humans in order to explore. We cannot just rely on robots forever. And the nice outcome of that, the big kumbaya moment, was that we met with Aborigine kids. And you could imagine Aborigine kids were not very, very interested about, spacesuit and astronauts. On the contrary, these guys were taking pictures of us, were interacting, were very, very curious. And hold on a little bit on that thought. because, well, they were super cool. And we have a police guy that came for arresting an astronaut, arresting innocent stromatolites. This was the title of the newspaper. The fact was that this guy was a policeman. He drove for 400 miles when he heard that we were there. So he had to come. And then, was kind of interesting things. And Nullagine is Aborigine territory in the Western Australia, where the stromatolites are. Well, stromatolites, where they are fossils, the scientists do believe that they are, the first fossilized proxy, visible proxy for life on our planet. So, discussion between geologists and astrobiologists. Another example is in South Africa. Sorry, guys. Okay, can we go back because I got stuck? Thank you. Okay, this one. This was an expedition to the Namib Desert. So why the Namib Desert? I just mentioned that this is an ecosystem sustained by fog, mostly. And this is the red sand. It's called the sand sea. And they're red because the fog interact with the surface of the sand and produce minerals called hematite. And these minerals are also present on Mars. That gives to some Martian the Mars sands that are red stripes. And here we have a teacher that she's looking at samples that we collected. So we were doing some training in microbiology and life detection and using microscopes. And here I think was Chris McKay wandering around, and we use him as a scale because he's pretty tall, the guy. So here's a look from the airplane. I was very fond of it because it's the sand sea, and you see this light tone strike. Okay, this is clay. This clay has been deposited by flash flood. And you get, sometimes when it rains, because sometimes it rained too, you get this river, this ephemeral river that in the end they found dunes, so they get dumped by dunes. So the water starts ponding between the dunes. And these are very interesting places where ephemeral lakes could be found. Another interesting place was Zealand. So New Zealand, we went to the Northern Island. Still more or less the same people. We start having alumni, so we have a teacher that sometimes they are the initiators. They begin to organize this expedition, and we ended up being the same people plus new people, old friends. We become friends in the end, and it's just very, very interesting how this legacy grows over time, even with not too much funding. Sometimes we run this expedition on our self-supported funding. So what we did is going to New Zealand. Why? Because it's a volcanic region, so was the Northern Island. And could we go back to the previous one? Okay, so this is where we are, Taiapo area. This is Auckland, and here is Auckland. And here, this is a volcanic area, region, where we have a lot of hydrothermal systems. So we have acidic and alkaline systems with a concoction, a combination of minerals that we found on Mars. Also, we have boiling waters where we have life and microbes living there. These are wonderful analogs for other planets where we have boiling water and life mixed with these minerals. And believe me, living at 2 and 3 pH or 10, 11 pH is a very, very hard life. Plus, the mineral environment sometimes tends to kill microbes. This is a struggle. What can help microbes as a source of nutrients can also kill them, because sometimes the precipitation in these systems tends to fossilize these microbes when they are still alive, and they have to grow faster and not to get entombed by their very own food. So it's kind of like strange life. So we went there and we were testing life detection. So the main problem is that when you look at microbes or even at molecules, you have to deal with a lot of things. Most important is, remember, the microbes really love living with their tiny minerals around. So they're very much attached to these minerals. So when I'm looking for organics or even for salts, I have to deal with a lot of things. I have to deal with the clay. I have to deal with the iron oxide. I have to deal with the sulfur. And most of the time, I see minerals, but I don't see life if life is hiding these minerals. So I have a high noise to signal ratio, where the noise is the mineral environment and the signal is the presence of life. It's a constant struggle. So we need to go to these places and try our life detection system to capture the truth, actually to get a science picture of where the cells are distributed in this environment. And this environment, can you see, is just 20 meters in length. This is a spring. And look at the order. We have something like lesser than 10 to 4, kind of like 1,000, 10,000. And the maximum could be up to 10 to 9. And everything between. And here is a colder water, this is hotter water, and the lower is where you have a hotter water around 100 Celsius degree. And the higher you have where you have a super green carpet farther away from the center, from the hot water. And this is, in order to get this number, I had to run every single sample about 20 times. And after these 20 times, I was getting zero value because I was struggling with too acid, too salty, too plenty of sulfur, too plenty of clay, too plenty of something. So this number is selected numbers from a zoo of bad and good numbers. This is why we're doing this in as many different environments under as many different conditions. So this is just Mojave Desert, or Death Valley National Park, California coast, Santa Barbara, just around here. This is the desert, and Death Valley is a place, the hottest, one of the hottest places on Earth, where in summer we have about 50 Celsius degree, it's about 126, actually 153 in 2012, and can be in winter as low as minus 16 in the place where I do conduct research. And again, it's very dry because the moisture that comes from the North Pacific during the winter storm or the summer storms have to jump different mountains, including the Sierras. So when the air gets here from here, it's progressively drier. So a little bit like in the Atacama. So we do rover testing there. This has been trials we've been doing in Cima Mountain. We're in Cima lava bed, where we have lava bed that we have also Mars, to see how the rover could negotiate to move in this rugged terrain. And here is the place where I do conduct research. It's called UBHB Volcanic Crater. It's situated in the northern part of that valley. Why is it interesting? Because we have many different environments. Geological terrain, like morphology, is cratered. Then have these layers. These layers are made by ancient rivers and ancient lake, like the one we saw on Mars. And even the same material, sandstone and claystone, where I took the picture you saw at the beginning. And you can see clays that are the results of a flash flood. And I look at life after flash flood, and not only how life persists and come back to life, kind of like life coming back to life, but also the environmental context is very important. What are the extreme temperature? Because when life comes back, I might not be there. And my instruments sometimes don't see that. So remember the picture with the little microbes I showed you? Those were noticed by me because I was there when it happened. Those microbes went away in about a few hours. And there was no way to detect those just by going there and collecting a sample. So I needed to be there. So this is why humans are so important for exploration. Being there at the right time, with a short time scale, is critical for achieving information behind your instruments, your tool, understanding and the context. Context is the most important thing. So just to give you an idea about in the crater, okay, this is that valley, mountain area. So here's the Remo crater. Here we have a mixture of minerals, like the ones that you can find on Mars, hematite and gypsum and sulfur and goethite that form on Mars. So this is a mineral-like environment, Mars-like mineral, okay? So you saw different examples, geology, sediments, and minerals, and extreme for life in terms of presence and distribution of water. So I think we can skip this one. It's about mineral composition and physical-chemical composition, environmental factors. These three things concur all together on making our life of planetary scientists and astrobiology very hard in terms of detection. This is why we cannot see life, because minerals and different ways minerals and water interact together with life. It's not a simple matter. Sometimes we think that just having a big set of instruments are very sensitive, very advanced. We have very advanced life detection systems nowadays. They can see a lot of things, but sometimes it's very difficult to figure out if we're looking at false negative or false positive. And particularly false negative. We do believe we don't see anything, not because there's nothing in there, but just because our sensitive, sophisticated billion-dollar instruments are not able to see them. So we are still important going outside in the heat or in the cold for figuring out these things in person. So this is a system I'm using for looking at this biomolecule here. Look, basically, we have a self. Remember cyanobacteria? On the external part of the cell, we have these molecules. It's like a sandwich, but what they're looking at is an inner part of membrane. And these molecules could be detected with an in situ assay. It's called lab on the chip, because all the things that you would do in a lab are miniaturized in a small chip, okay? It does everything. Yet, if it's too salty, you won't see anything. So you need to dilute your sample. Or if it's too much sulfur, you need to get rid of the sulfur, and on and on and on. Every single sample from any of those environments I've shown you is a challenge. Instruments are cool. It's just you need to try very hard and harder and harder. And sometimes you can even go farther because there are some barriers in terms of analysis. There are some analytical issues that are difficult to overcome. You just have to give up or try harder a little bit later. Think about, this is just a table that gives you an idea, okay, you have seen all the environments, okay? So this is the Atacama Desert. Here's the California coast. Between there is the Namib Desert, the Ubehebe Crater in the Mojave Desert, and Australia. Okay, Australian sample. Here is the number of cells. So here's lower 1,000, this is million, and these are billions. You can see that increasing the precipitation, so from the most arid to the most wet, we have an increase in the biomass. But this increase also depends on the minerals where we are detecting those microbes. So part of my work is also looking at different materials to see how much the different minerals do affect the life detection. So in the last expedition, I think we can run the movie, and so you get an idea of what happened in that. And by the way, this movie is already still under embargo. This is why you don't find it.
The beauty of scientific investigations that brings scientists from all over the world with a bunch of different disciplines, and we learn from each other, we learn from our culture, and it's so important to do this. Because when humanity goes to explore space, it's not going to be America or India or China or Russia, it's going to be humanity that explores this. So having this this international collaborations happening like we're having now at Spaceward Bound is so important to develop.
What India has to offer up here in the dark is a high altitude, cold desert. And there's not many of these in the world.
Other expeditions were small expeditions. This is quite big, 32 people at a time. We've never been here.
तो हम ऐसी चीज़ों को ढूंढने की कोशिश कर रहे हैं कि हम एक सेट पैरामीटर जानते हैं कि इस पैरामीटर में ही लाइफ सर्वाइव करती है, उससे बियॉन्ड भी जाकर के हम लाइफ देख सकते हैं.
It was terrific to go to Setball School today.
The paper rocket.
The kids really loved it, even on their rockets today. For kids to put their own name onto something that they've made, it shows that they've got pride. Kids love it when you give them the chance to do an experiment or make and design something for themselves.
We're going up, we want to go to the Nubra Valley, we've got to go over the big pass. I know we've got to go up another 2,000 feet more. Oh my God.
We started our day by doing yoga. Because we are at such a high elevation, practicing yoga every day actually helped most of us continue working throughout the day. We used to start pretty early at like 7 o'clock or 8 o'clock in the morning and reach the site by 11:30 and then work pretty much whole day and get back.
Part of my work is getting several samples aimed from different environments, particularly also the snow, or the permafrost, or the ice, all as many samples matters.
As a geologist, having never been here before, I look out the window and I want to go there. You know, that's just it. I want to go everywhere. Maybe Tata Motors can take me there.
The dark is just incredible from like a geology point of view. Your vehicle is your lifeline, you know, like you're totally dependent on getting out there and getting back. I'm working in hot springs environments that are really dangerous. There's water that's up to 85 degrees, so I have any emergencies at all, I'm relying on my team and my vehicle to get me out of there safely.
I have my students, my high school students, make these tiles, see what grows under them. I have these all over the world. The personal goal is to deploy a set of these in the dock.
The main goal of this expedition for us was the main core of the technology that will be part of the Habit instrument that will be flying into ExoMars 2020 mission. In Sogar Lake, we have a really big beach of salt. We don't know if we will discover something new, but at least it was a really good Mars analog with natural salts.
This small little region has a very diverse set of geography and geology, and with that, probably a very diverse set of microbiological organisms, which is the major focus of many of the groups here at Spaceward Bound.
Just such an amazing experience. I can't pick out anything that's been especially special. The people have been wonderful. The places we've been have been very accommodating to us. The structure of this process of this program has been really good too. It's just and what we see here in every way is just beyond my imagination.
Scientists, we are crazy in a sense. Like, we love what we do, and we'll try to do whatever we can to get it done, right?
It's when you start a project and you finally see it happening in front of you, and you see all these people doing some work, and you're just standing there looking at it. So it's quite a fulfilling.